You know, getting into orbit is one of the most expensive, dangerous things we do. We're literally strapping people to controlled explosions, burning just unbelievable amounts of fuel with incredibly complex machines. But for more than 100 years, scientists and engineers have dreamed of a much simpler way, an elevator to space. So if the idea is that old, why don't we have one?
I mean, just imagine it for a second. No rockets, no bone-rattling launch. Instead, you just step into a cabin, a climber, and you go up. Smoothly, quietly. You could take your time, maybe even stop for the view. It's a concept that would completely fundamentally change our relationship with space.
And the biggest reason this idea just won't go away? The economics are staggering. Right now, launching a single kilogram of anything into orbit costs thousands of dollars. A space elevator? Well, projections say it would slash that cost by 95%. Access to space would become routine, not this once-in-a-lifetime revolutionary event.
Okay, so what would this thing actually look like? The modern idea is a really elegant solution to a dream that's been kicking around for over a century.
It all started way back in 1895. One of the fathers of rocketry, Konstantin Tsiolkovsky, was looking at the brand new Eiffel Tower and thought, hey, what if we just built a tower all the way to space? Of course, we now know no material could ever support its own weight like that. So today, the idea is flipped on its head. It's not a tower pushing up from the ground, but a super strong cable hanging down from orbit, held perfectly in place by the simple physics of our spinning planet.
So here's the big question. How does a cable that's thousands upon thousands of kilometers long just stay up there? Why doesn't it just come crashing down? Well, it all comes down to a very clever cosmic balancing act. Think about swinging a ball on a string around your head. Your hand is like Earth's gravity, constantly pulling the ball in. But the spinning motion creates that outward force, the centrifugal force, that keeps the string tight, right? A space elevator works exactly the same way. Gravity is always pulling it down, but because the Earth is spinning, there's a constant force trying to fling it out into space. The whole trick is finding the perfect spot where those two forces cancel each other out. And that perfect balancing point has a name: geostationary orbit. At exactly 35,786 kilometers up, right over the equator, an object orbits at the same speed the Earth is spinning. So from the ground, it just looks like it's hanging there, motionless in the sky. This is our anchor point. You'd have a big counterweight, maybe even a captured asteroid, way out past this point, and the cable would unspool all the way down to the surface, held perfectly taut by physics.
So the physics checks out. The concept is sound. And sure, there are other huge challenges, like how do you avoid space debris? How do you power the climbers? What about bad weather at the base? But all of those, they kind of pale in comparison to the one single monumental problem: the cable itself. Just to understand the sheer scale of this challenge, let's do a little thought experiment. We're really good at making steel. It's strong, we know how it works, so what if we just tried to build the cable out of steel? You see, a steel cable doesn't just have to support a climber. It has to support its own immense weight, stretching for tens of thousands of kilometers. And the math shows that at its most stressed point, the cable would need to handle nearly 400,000 megapascals of force. Our absolute best, strongest steel alloys top out at around 5,000. It's not even close. It would snap under its own weight long before it ever reached orbit.
Okay, so what if you get clever? You can make the cable tapered, right? Thicker at the top where the stress is highest. But even that doesn't work for steel. To handle the load, a steel cable, starting as thin as a guitar string on the ground, would have to be wider than the entire observable universe by the time it got to the counterweight. It is just physically impossible.
So, steel is out. Kevlar is out. All of our conventional supermaterials are totally out. To build a space elevator, we need something that feels like it's straight out of science fiction. We need a material that is both unbelievably strong and impossibly lightweight.
And this brings us to the leading candidate for that miracle material: carbon nanotubes. Just picture this. You take a sheet of carbon that's only one single atom thick. That's called graphene. Now you roll that sheet up into a microscopic perfect tube. What you get is a material with properties that are almost hard to believe.
Steel is strong, sure, but it's also really heavy. Its specific strength, that's its strength-to-weight ratio, is pretty low. Carbon nanotubes, or CNTs, are the exact opposite. They are unbelievably strong and ridiculously light. If we can make a cable out of them, that insane taper ratio we talked about, the one that was bigger than the universe, drops to just 1.6. Suddenly, the impossible starts to look, well, possible. So problem solved, right? Let's start building. Well, not so fast. There is a huge, huge gap between what works in a lab and what works in reality. See, the incredible strength of a nanotube relies on it being atomically perfect. But when we try to make long strands of them, they tend to get tangled up, they have defects, and their strength just plummets. Right now, the longest we've made is about a meter. We need millions of meters, all perfectly aligned. We're just not there yet.
But even with this massive materials hurdle, the dream is very, very much alive. So the question becomes not just what we'll build it out of, but also where and when.
What if we just change the location? Let's talk about the Moon or Mars. The gravity on those worlds is so much weaker that it dramatically lowers the requirements for the material. We could actually build a space elevator on the Moon right now with materials we already have, like Kevlar. The problem just shifts from a material science challenge to a pure logistics challenge. How do you get all that stuff to another world to build it?
And yet, the pull of an Earth-based elevator is so strong that the race is on. This isn't just a thought experiment anymore. Major corporations, even entire nations, are pouring money into this research. Companies in both China and Japan have publicly said they want to have one running by 2050. They're making a huge bet that we are going to solve this materials problem in the next couple of decades.
And that leaves us with this one fascinating final question. What challenge will we conquer first? The mind-bending difficulty of creating a true miracle material right here on Earth, or the immense logistical nightmare of building in space? The answer to that is going to define the next chapter of our journey to the stars.